Okay, so moving on to the next talk, we have Hui Li, who will be presenting on tropical cyclones and high resolution modeling. It's a shorter talk, these ones, they're like 15 minutes. We'll have a little bit of time for questions after that. This is Hui's research. No, come on. Yeah, so here we go, Hui, thank you.
Hi, everyone, I'm Hui. So today I'm going to talk about how I use CESM in my own research. So my research focus is on tropical cyclones and climate. So when you think about this relationship, most of the times you'll think how the larger scale climate can affect tropical cyclone activity. That's a very interesting topic, and a lot of research effort has been put into that aspect. But there is another aspect to this question. So the question we're trying to answer in my research is, can tropical cyclones affect the larger scale climate? So basically we're asking, can these extreme weather events have a effect on the larger scale and bigger scale climate phenomenon? I just use this. Okay. The fundamental physics behind these hypotheses lies in the relationship between tropical cyclones and the upper ocean. So there's a two-way interaction between the two. On the one hand, the ocean can provide heat energy to tropical cyclones through the enthalpy fluxes, so they can fuel the storms. And on the other hand, TCs can provide mechanical energy to the ocean through this strong wind forcing. So it is this mechanical energy that TCs put into the ocean that really matters for how TC can affect our climate. So how it works is that when a tropical cyclone moves over the ocean surface, it can cause a strong upper ocean mixing. And this mixing process would try to homogenize the upper ocean, right? And it would bring up the cold water to the near surface and pump down warm water into the ocean interior. That's why oftentimes we will see a SST cold wake following the tropical cyclone tracks. So after this mixing process, this little panel here shows the vertical temperature profile before a tropical cyclone in black and after a tropical cyclone in gray. So we see that after the mixing, the profile has changed, and this panel here shows the temperature anomaly due to this change. So we see after the mixing, there's a cold temperature anomaly at the upper ocean and a warm temperature anomaly beneath the ocean thermocline. Okay, so we got this ocean temperature anomaly dipole. And then after about 30 to 60 days, this cold temperature anomaly at the near surface could be restored to pre-storm climatological condition through this heat flux adjustment. But this warm temperature anomaly that was shielded from the surface influences because they're in the ocean thermocline, they will stay there for a much longer time, beyond 6 months, actually. So this tells us this turbulent ocean vertical mixing induced by tropical cyclones can give us a net heat gain into the ocean. And this is very important. Research through the years have found that through this process, tropical cyclones can have the potential to alter your ocean heat content and heat transport, and also affect temperature patterns, seasonal cycles of the SST, and the mixed layer depth. So it's important to understand tropical cyclones' contribution to the climate system because it can help us constrain uncertainties in our climate simulations and projections. However, this TC's impact have not been explored in a fully coupled global Earth system model. So that's kind of what I want to do here. So that's the goal of the current research. Yes, so in order to achieve this, we're going to use two configurations of the CESM. So one of them is the very high resolution CESM model. The very high resolution in climate model here, I mean, is 1/4 of a degree atmosphere or 25 kilometer resolution. So in this resolution, the model itself can generate their own tropical cyclones, which is pretty cool. Let me see if this animation could work. Or do I animate? Nope. Okay. Oh, very good. So yeah, this visualization I made. So this vectors you're seeing is the atmosphere bottom wind simulated in this high resolution 1/4 of a degree atmosphere model. So you can see as the model integrates, there are some tropical cyclones emerging. So remember this, we didn't really put in any disturbances or any seas or whatever. These storms just emerge by themselves as the model integrates because they have enough resolution. At the same time, the colors in the ocean area is the temperature anomaly induced by the storms in another ocean simulation that I ran. So we can see that this model can also produce these cold SST, cold wake we saw in the observations. This tells us that the model can capture this TC ocean interaction reasonably well. If we run, after we run the model, we're gonna find all these tropical cyclones simulated in the model. And we see that the climatological TC statistics actually very similar to the observations. So the top panel shows this 30 years of tropical cyclone tracks in the observations, and bottom is from this high resolution model. So we see that the model can simulate the geographical distribution of the TCs, generally consistent with the observation, and also the range of the storm intensity to some extent. However, there is some bias. For the high resolution model will not be able to resolve a lot of category 5 super intense storms. And also there's, notoriously there's a low bias in the North Atlantic phasing. Okay, so that was that. And we also want to make sure if, the subsurface processes are resolved in the model, right? Because, the heat gain in the ocean is what matters for the atmosphere in the long term. So we're going to examine that here. Okay, so this animation, we're looking at the 3D ocean in the Western tropical Pacific. Again, the surface vectors are the wind from the atmosphere bottom. So we see there is a storm forming over here. And in the ocean, we see that, okay, there is a cold temperature anomaly at the surface and also in the upper ocean, and a warm temperature anomaly gradually forms in the ocean thermocline right here. And as the storm moves west, this warm temperature anomaly just stays here, and it stays there robustly. And as the moves on, some cold anomaly that was originally here has already, gone back to the normal condition, but the warm temperature anomaly here stays for much longer. So this tells us, again, the model is able to simulate the ocean's responses to this tropical cyclone forcing. Okay, so that was all at the regional scale, right? So here we're going to looking at a bigger spatial scale and look at how TCs may impact the ocean from this perspective. So here in this animation, we're looking at the Pacific. We're going to see a ocean temperature from in both the surface and subsurface. Yes, okay. So now the moving black dots are the tropical cyclones we put into the ocean model. The yellow and blue are the warm versus cold temperature anomalies. So we can see, okay, this is what's really cool. There was a storm, early season storm happening in the Western Pacific, then actually excites this equatorial Kelvin wave. So these Kelvin waves can move really rapidly across the equatorial Pacific Ocean and carrying with them the warm temperature anomaly induced by the storm. So in this way, the TCs can have this mechanism that has a very rapid heat transport from the west to the east. So this is kind of conducive to El Nino-like SST pattern. So this is something that's pretty cool, I think. So back to how we're going to address how tropical cyclones affect climate in this fully coupled model. So we said we're going to utilize this high resolution model as well as a low resolution model because we want to have a control where there's no tropical cyclone effect, right? So this low resolution model we're talking about was using this 1 degree. It's not actually that low, but it doesn't really resolve strong TC events. So what we're going to do in this experiment is that we're going to, first of all, find all the TCs in this high resolution model that we saw it can simulate global TC statistics, consistent with observations. And then we're gonna, for each time step, we're gonna take snapshots of this TC winds and compile this TC wind forcing inventory. And then we're gonna add this TC winds to this low resolution control simulation, and also preserving their original timing and locations. So this low resolution configuration with added TC winds, we call it a low res TC run. It is run for 100 years. And it will be compared to the low res control run without TC's impact, also 100 years. So we can diagnose the impact of TC wind forcing within this coupled climate system by comparing this low res TC run and a low res control run. So just moving on to what we found. So at the last 30 years of the simulation, we found there are some significant changes of SST, first of all. So we find a warm temperature pattern in the mid-latitude around the subtropical gyres in the ocean. And there's also a warm temperature anomaly signal in the eastern equatorial Pacific. We also found interesting changes in the surface heat flux patterns. Here, this figure shows the total heat flux. Positive means it goes into the ocean. So we see an increased heat flux in the Indo-Pacific warm pool area, and some increased heat release to the atmosphere in the corrosional region, as well as in the eastern equatorial Pacific. And there's some heat gain in the North Atlantic as well, some remote effects of TCs. And also some changes in precipitation, some drying in the Western Pacific and Indo-Pacific Ocean, and some wettening in the central to eastern equatorial Pacific. And there are some significant changes in the ocean subsurface temperature. So we find these tropical cyclones in the couple model can induce this temperature anomaly pattern. So this is the cross-section in the equatorial Pacific. The x-axis is longitude, y-axis is depth. So what we're saying here is that TC can induce this warming signal across the Pacific Ocean in the ocean thermocline area. And the warming is most significant in the Eastern Pacific. And also the panel down here shows the meridional cross section. So there's a warm temperature anomaly in the mid latitude and also in the mid deep tropics. So that was the changes in the SST temperature and stuff. But here we also look at changes in the dynamics. For the ocean, we find that the TCs can actually increase the global meridional overturning circulation. So this is the climatological condition in the global meridional overturning circulation. So this is the anomaly. So we find that the added TC winds can strengthen this thing called a subtropical sail. It's the overturning in the ocean. But for the Atlantic, this is the climatology, this is the anomaly. We found there's a slowdown of the Atlantic meridional overturning circulation, the AMOC. And also there's changes in meridional ocean heat transport. This blue line shows the climatological conditions and the black shows the anomaly. So we find that these TC winds, after we add into the model, they can increase the poleward heat transport at the subtropics. And also there is increased heat convergence at the deep tropics. Let's see. Okay, so we talked a little bit about how TCs may potentially affect ENSO. So we actually look at the ENSO statistics in the model. So here is the Nino 3.4 time index. So we find that when you're adding TCs, they can actually increase the standard deviation of the El Nino seasonal cycle. And they can also shift the El Nino frequency. Black is observation, blue is control, red is after we adding TC. So the ENSO power has increased, but you can see the shape of the frequency is actually more consistent with the observations when we compare to the control. And also we found that when you're adding TCs, your El Nino strength is gonna get enhanced. So here we're looking at the SST distribution of each and every El Nino events. Blue showing the events in the control, the red are the events in the TC run. So just by eyeballing, we see that TC run has a lot more warming signals during El Nino. And also there is interestingly, a very robust positive correlation between strong El Nino events and the near equator TC wind power. So this confirms that tropical cyclones can indeed enhance ENSO strength. That is all I want to show you. In summary, we kind of try to examine the impact of tropical cyclones on the climate in a fully coupled climate model. So we designed an experiment in order to achieve that. We find that these added TC winds in the fully coupled model can impact the global SST and lead to changes in surface heat fluxes and precipitation. And they also have some dynamical effect on the ocean. It changes the ocean meridional heat transport and overturning circulation strength. And also the TCs can interestingly increase the ENSO power and shift the ENSO frequency. And also they lead to more strong to extreme El Nino events. Yes, so that's all I have for today's talk. Thank you.
Thanks, Beck. We have a couple of minutes for questions. If anyone wants to have a question, please come to the microphone.
Hi, great talk. So I had a question about this high resolution model and the way it's able to characterize these intraseasonal weather events. Is it also able to capture like MJO or the monsoon intraseasonal oscillations better as well?
I think there was some problem with the monsoon. with the MJO.
Okay.
And I think it's a work in progress. I'm not very familiar with the MJO simulation, but from the seminars I've been, people are trying to look at if the stratosphere, if you're adding the stratosphere, if the MJO could be improved. So, it's not always perfect. Even for tropical cyclones, it's not perfect.
I guess I just wonder, so you showed that it had improved skill for dynamics and other things, right? If
Mm.
that's related to some of these other intraseasonal, like westerly wind bursts or other patterns you're able to better represent in these high resolution atmosphere models.
Right, that's a great question. I think compared to low resolution, it's definitely a big improvement.
Sure, of
Yeah,
course. Yeah.
but
Yeah.
yeah, but other than that, I don't know much about MJO and other interseasonal variability. So
Okay. Thank you.
yeah.
Thank you very much for your talk. I'm wondering if there is tropical cyclone in the free run of the coarse resolution, or is the wind speed is just smeared out in a coarser grid, so it cannot generate tropical cyclone.
So actually, if you look at the 1 degree model, you can still see some, we call it tropical cyclone-like circulations. These so-called circulations, they have a much bigger spatial scale than the real tropical cyclones, and their intensity is going to be much lower. So for TC, sometimes we define if your surface wind speed is bigger than, for example, 17 meters per second, then you're a storm. But if we use this definition, we won't see much in the 1 degree model. So the resolution is not enough to resolve the strong winds.
And also maybe a technical question, what processes do you transfer the high resolution velocity to the coarse resolution? Do you coarse grain them, or does it harm the velocity when you move the high resolution velocity to the low?
Yeah, that's a great question. So when we do it, we try to mimic the behavior in the fully coupled model. So if we're going to see the effect in the fully coupled model itself, how it would look like, right? So in the fully coupled high resolution, we're using a 1/4 degree atmosphere coupled to 1 degree ocean. So in this process, the surface wind will first be interpolated on the ocean grid anyway. So in this process, the wind is definitely, as you said, will be compromised a little. So in this experiment, because we want to mimic that, we repeated this process. We have to coarse grain them into the 1 degree ocean grid, to do the experiment. But even for this, sacrifice, you still get very strong signals of TC's impact on the ocean. So, but that's something we should think about, how to, preserve the original TC strength.
Thank you very much.
Yeah.
One more question.
I was curious if you had plans to do a high resolution run for the future climate, because it'd be really interesting to see what the effect of tropical cyclones are on the future climate. And CSM has this really interesting ENSO behavior over time in the future climate, and it'd be really interesting to see the effect of tropical cyclones on that.
Yes, actually, this is my next plan.
Great.
It's in my journal. Yes, definitely. That would be a very interesting question to see in future how TCs may influence El Nino changes.